All right, let's take a look at some slope fields. Okay, so slope fields is probably a new concept for everyone. Slope fields are useful in helping us to solve differential equations. All right, so a differential equation is like this one, an equation with a derivative already in it. Okay, so let me show you how a slope field works and how to create one. All right, so what a slope field is going to do is give us all the possible slopes of the curve if it were to go through all these different points. Now, obviously, you can't go through all of them, but it'll help us figure out what the solution looks like. And the solution to a differential equation is an equation for a curve that doesn't have a derivative in it anymore. Okay, so what we do is we just look at all these points on this field, and we just start picking them. Here's one, 1, 1. All right, so remember, dy dx, a derivative, is just the slope, right? Slope of the tangent line. It's the change in y over the change in x, and that's just slope. So they're telling us that the slope equals x over y. So here, x is 1, y is 1. So the slope here is going to be 1 over 1, which is 1. All right, how about this point right here? Slope is x over y. 2 over 1. Slope is 2. 1, 2, so our slope is like that. All right, so I'm just putting little tick marks to represent the slope. Here the slope is 3 over 1, 4 over 1, 5 over 1. All right, so the idea behind a slope field is to hit up all these different points. And I know you're probably thinking, oh, really? That's a lot of points. And it is, but you won't always have to do it by hand, and you won't always have to do this many points, but you'll also see that a lot of patterns start to emerge. Let me show you an example of a pattern. All right, let's look at this point right here. All right, so it's x over y. 0 over 1 is 0, right? 0 over 2 is 0. 0 over 3, 0 over 4, 0 over 5. What about 0 over 0? Not 0, right? Undefined. And undefined is vertical slope, right? But then we're back to negative 1 over 0. I'm sorry, 0 over negative 1, 0 over negative 2, 0 over negative 3, 0 over negative 4, 0 over negative 5. All those slopes are 0. And let's look at this guy. 1 over 0, undefined. 2 over 0, undefined. Undefined, undefined, undefined. Undefined, 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 undefined. All right, more patterns. 1 over 1 is 1. 2 over 2 is 1. 3 over 3 is 1. 4 over 4 is 1. 5 over 5 is 1. Negative 1 over negative 1 is 1. Negative 2 over negative 2, 1. Continue, continue, continue. Sorry. How about 1 over negative 1? Negative 1. 2 over negative 2, negative 1. So we can continue this pattern. All right. And you'll see that a lot of other patterns emerge. But let's just put in a few other points just so that we can be sure that we understand how a slope field works. Random point, this one. X over y is the slope, right? Remember, x over y is the slope. Negative 4 over 2. So negative 2 is the slope. So we can do that one. Let's pick this one. 2 over negative 4. So that's negative 1/2. So it's going to look like this. Okay, and once again, these slopes don't have to be perfectly accurate. We just want them to be estimates so we can get a picture of what it looks like. And if we continue to do this, you'll see a lot of patterns emerging, and so it'll go pretty quick. But if we continue, our slope field should look like this. All right, so with a little help from technology, our slope field should look like this. And notice that's pretty much exactly what we got before, right? Verticals here, horizontals here, slope of 1 on this diagonal, slope of negative 1 on this diagonal, and then everything in between. All right, so let's think about how this actually helps us, right? This doesn't tell us exactly what the solution is, but it tells us what the solutions might be, right? I mean, it kind of looks like hyperbolas, right? Doesn't this kind of look like a hyperbola? So let's put in the equation of a hyperbola, which you may not remember. The equation of a hyperbola is similar to a circle, except instead of doing x squared plus y squared, we do x squared minus y squared, or y squared minus x squared. But I'm going to go with x squared minus y squared. And then that always equals some sort of constant. In this case, I'm just going to say 1. Definitely looks like the slope of this hyperbola is matching the slope in the slope fields, right? So we have really good reason to think that the solution to the differential equation of this differential equation right here is going to be the equation of a hyperbola. So we thought the solution might be something like this: x squared minus y squared equals 1. How can we test that? Well, do you guys remember implicit differentiation? Let's give that a shot. So we're going to take the derivative of both sides with respect to x. Remember, the derivative of a constant is 0. And remember, when we take the derivative with respect to x of something with y, we got to chain rule it. All right, so now let's solve for y prime. So let's subtract 2x from both sides. And let's divide by negative 2y. We get y prime, which is really the same thing as dy dx, right? Just different notation, equals x over y. All right, so we've used our slope field to say, hey, maybe the solution is a hyperbola. And a hyperbola works, right? Now, we chose arbitrary constants, but the constants will kind of fall out anyway, because when we take the derivative of a constant, it's always 0, right? So this differential equation tells us that we're referring to a hyperbola. We don't know which hyperbola. It could be many hyperbolas, but the solution to this differential equation is a hyperbola. So x squared minus y squared equals 1 is a solution. X squared minus y squared equals 2 is a solution. And x squared minus y squared equals 100. That's also a solution. Okay, so all of those are solutions to this differential equation. Okay, I realize that this is a confusing concept and that it's totally new, so please write down any questions you have and we'll talk about them tomorrow. See ya.